Okay, let's get started. So, this is not my Halloween costume. I had some retinal surgery, and it's going to take a little while to recover, so I'll probably still have problems when we come back next week. But what I wanted to do today is just go through these notes, and the importance of doing this is to make sure that you can do the homework assignment that's due. I think it's due today 2 weeks, is that right? Thursday, so today 2 weeks and 2 days. 16 days from now. Beg pardon? No, it's not. So I guess then it's 11, and then I guess there's next week, so it's 9 days from now. Yeah. I mean, I don't care, but I didn't want to go into your dead week. Who wants it due over dead week rather than? Okay. Sure. It's okay. That's fine. Then I'll reschedule it then next. I'll send out an email about that. I guess Colin and Eric aren't here. So we've been talking about stochastic models and Monte Carlo models. Well, Monte Carlo methods. So stochastic model is every time you run a model, you get a slightly different answer. And we've seen a couple of models like that, and we've seen how to generate sequences of random numbers. And we talked about a very simple process last week of extinction statistics. And then also I talked a little bit about population viability analysis. So population viability analysis is a methodology for having a look at populations and trying to assess the probability that they're going to go extinct under certain conditions. And so what you do is you make a model of a population, and you assess the probability that the population might go extinct in the next 100 years. And then you perform some management strategy. So, for example, it may be an endangered species, and it may be that if you protect some areas of old-growth forest, like in the spotted owl. How many of you remember the spotted owl situation about a decade or so ago, when people were talking about conserving spotted owl and saving the redwoods? So if you set land aside, and instead of logging it, so you can say, okay, I'll make a model, and if I log this area, I know that the carrying capacity for the spotted owl will be lower, and I build a model, and I have a look at the risk associated with the spotted owl population going extinct over the next 100 years. And then if I set aside some land, some reserves, and I redo that analysis, then I can assess the risk again. And the model will tell you something like, okay, over the next 100 years, if you don't set aside some area and you log it, maybe there'll be a 30% probability of the population going extinct over the next 100 years. And if you do set it aside, maybe there'll only be a 2 or 3% probability. And then based on that assessment, you decide whether it's worth the investment and what you want to do about that. So one of the main tools we have is to use the binomial theorem, or the binomial model. And so, for example, the binomial model is useful if we're asking the question, what's the probability, if we have 40 individuals and they each have a certain probability of surviving the next time interval, how many will actually survive? And it's like throwing a 40-sided set of dice and seeing what number comes up. And the number that comes up conforms to the binomial probability. And the binomial has two parameters. The one parameter is the largest number that can come up. So the smallest number that can come up is 0, the largest number that can come up. And then the probability in that number, if you've got n possible events, and they can all be positive, some of them may be negative with a certain probability, what is that probability? And so this is a number p. But for example, if you expect the number of individuals that will survive to be b of m, that means p is going to be b over m. So if I've got 40 individuals and I expect 10 of them I expect 30 of them to survive, then that means 30 out of 40 are expected to survive. So I said p equal to 30 out of 40, which is 0.75. And then when I make a drawing from the binomial theorem, and I use the binomial theorem, sometimes I'll get 30, sometimes 29, 28, sometimes 31, 32, and the number that comes up will follow a binomial distribution. And it's only with a very low probability that, for example, only 2 or 3 might survive, or 39 out of 40 might survive. So for example, if m is equal to 3, so if we're talking about litter sizes, and I spoke a little bit about this last week, and I said if an individual can have anywhere from 0 to, let's say, 3 individuals in a litter, but they expect to have on average 2, then you'd put 3 over here and 2 over there, so this would be 3 and 2/3. And then the probability that the litter would be of size 0 would be 1 over 27. It would be of size 1 would be 6 over 27, so you can use the binomial expansion to get these numbers. That it would be of size 2 would be 12 over 27, and then it would be of size 3, it would be 8 over 27. Yeah? Yeah, b would be the expected. But in the binomial theorem, what you're putting is m and p, not m and b. So I'm constructing a p by saying that the way you calculate p is to calculate the actual expected size, the expected number of the total number, which gives you the expected proportion p. Now, population viability analysis, in the simplest of models, remember we said if you have a Semel-Paris model with a synchronized population and you have n individuals, and you can think of n butterflies all laying eggs, and they each lay on average b eggs. And then each one of those eggs has a certain probability s of making it to an adult. Then n plus 1 would be the number of new adults. And if you also remember, we talked about, in most of these models, we're thinking about females per female, the number of female young per female, assuming that males, we can make assumptions that we're not interested in the males, or the males are equal sex ratio. So if I wanted to turn the top model here, n of t plus 1 equals sb times n of t, into a binomial model, if I'm only interested in the binomial probability of the survival, so if I say everybody has the same number of eggs, b, so that's not demographic stochasticity, that's a fixed number, then I would say n of t plus 1 is binomial. This is the number of eggs, and this is the probability that each survives. But if you also want to make the number of eggs a stochastic variable, then what you have to do is you say, okay, if each individual can have m eggs, and the expected number is b, then this would be m times n over t. So this is the total number of eggs that could be laid in the population. So as opposed to the first case over here, where I'm just thinking of a single individual, and I just have m, b upon m, if I have n individuals, and they're all satisfying the binomial, it's like instead of having m boxes to put eggs in, each individual has m boxes, so I have n times m of these boxes. And then each individual is going to fill, or not fill, m of them, with a probability b over m. Do you understand that? Okay. So then, this would be the expected number of eggs. So then instead of putting this number in over here, you calculate this variable first, and you put this variable as it comes up in here, and then you say each one of those eggs. So you've got two binomial calculations. First is the binomial calculations with the number of eggs that are laid, and then it's the binomial calculation with the proportion of eggs that survive. And so you can build that model. Now, one of the things that we talked about in modeling is we said, what happens if S is not a fixed constant, but if S is a density-dependent survival rate? So big S upon n is equal to little s, but little s actually goes down as n gets bigger and bigger. And you have this number k and this number g that sets the survival rate. So we've seen this function before. So here's s as a function of n, and here is little s. And instead of having a constant, what we have is a function that looks like this. And then k tells us where this point is that it turns over, and g tells us how rapidly it turns over. So for example, if g is a large number, then it'll look like a very steep effect. And if g is a smaller number, then it's a shallow effect. So you've seen that in the models we built. So now you can say I can put in density dependence as well. So if we put in density independence, as we did, we talked about in lecture 2, then we can get our model. And our model says, select the initial value that you start out with, then the number of eggs, x of t minus 1, is n of t minus 1 draws from this binomial distribution. And n of t minus 1 draws from this binomial distribution is the same as taking the binomial distribution and just putting the n of t minus 1 in there. Any questions about that, as we discussed? Okay? Yeah? Which two? Okay, so what I'm saying is that you have to draw this number x of t minus 1. And to get x of t minus 1, you use this equation over here. So this is n of t minus 1. Here I'm using x of t instead of x of t minus 1. This is n of t draws from the binomial distribution m b upon m. So I should have actually just written this as x of t minus 1. You draw it from the distribution binomial, little m times n of t minus 1, and then p is b upon m. So I'm telling you that you're drawing from this distribution n of t minus 1 times, which is the same as just drawing once from a binomial distribution with n of t minus 1 inside here. Now once you've done that, you've calculated the number of eggs. Then if you want to look at the density dependence, you use this equation. So to get the next binomial expression, you have x of t minus 1 individuals, all developing to adults, but only a proportion p of t of them are going to survive, and the proportion that survive depends on this density-dependent expression. So you can put this all together in a model. Any questions about that? Oh, okay. Now, and what we said is that these models are basically inadequate over here because they don't take age structure into account. So if you want to take age structure into account, you build a Leslie matrix model. Now here's a Leslie matrix model with 3 age classes. So I could build one with as many age classes as I need. In this Leslie matrix model, what I'm saying is that I'm going to put in density-dependent survival in the age class that goes from the young to the next age class. So you can say this is young, juveniles, and adults. So what's actually happening is in the young, going from young to juvenile, I'm saying that's where the density dependent comes in. And the reason why I'm doing this is that I'm going to take a marsupial population. In a marsupial population, the young are protected because they live in a pouch. But then after they get out of the pouch, they become vulnerable because of density dependence. So I've got the density dependent term in over here. I could put the density dependent term in anywhere in this equation. I could have more than one density dependent term. But this is where I'm going to put the density dependence. Now, if you remember in the fisheries model, we actually put the density dependence in the youngest age class. Remember, we had a stock recruitment relationship. So we put the density dependence in calculating x1 from x0. So we actually had the density dependence in at this level, but now I'm putting the density dependence in at the next level. So from a biologist point of view, you decide where is density dependence most likely to act. In some populations, density dependence is most likely to act on the oldest group. So for example, if you look at elk in Yellowstone, what happens there is you can have, say, age classes 1 to 10. And the last age class can be individuals that are 10 years and older, or 1 to 8. And then it turns out that the oldest age class, the probability that individuals in that age class survive the winter to come back is where the vulnerability is. So older individual, their teeth wear down. They can't graze as efficiently as younger individuals. And the density dependence can come in at the oldest age class. So again, the biology will tell you which age class is the most important. Now what I'm saying here is that the density dependence depends on a variable, which I call n, which is the total population size. So I'm saying that n at time t is the number of young plus juveniles plus adults. And this is a very simple way of incorporating density dependence. Its density dependence depends on the number of individuals. An even better way of incorporating density independence would be to have the relative weights of the individuals here. Because if they're depending through food, then you'd say that their relative weight is a better indicator, or their relative weight to some power, because younger individuals proportionately eat more for their relative weight. So you might adjust for that. But there may be some weighting so that younger individuals don't require as much, but per unit biomass they may require more. So you can do adjustments like that. I'm not going to go too much into this, because each one depends on the biology of the organism. Okay, so we say the total number of individuals in the population is given by just adding this up. And here we say the density-dependent effect, which is how much to reduce S1. We take S1 and we multiply it by this factor, Fn. And this factor, Fn, goes from being 1 at low densities when n, capital N, is much smaller than k, to a half when n is equal to k, to something that's close to 0 when n is much greater than k. So now what I'm saying that this model can be written out explicitly in the following way. You choose your initial values for each of the different age classes. And then you go through a loop where you start out with t equal to 0, and you go up to t equal to t minus 1, so that you finally calculate t at time capital, x at time capital T for all of these. And n is just the total population size. X0, which are the number of young that are born into the population. This is the number of young that are born to the oldest age class. This is the number of young born to the middle age class. And this is the number of young born to the lowest age class. And you'll see that in the data I give you, B1 is equal to 0. Because in the model, I'm saying that the youngest age class are not sexually mature. And then I've got B3 is much bigger than B2, because only a small proportion of the juveniles at the end of the season are ready to reproduce. Once you've calculated the number of new individuals that are produced within the season, you then say how many of these new individuals survive, and that depends on the S0. And that gives you your X1. Then your X2, what you have to do is you have to apply the binomial to X1 from the previous season, because these are the individuals that are aging, and these are the proportion S1 that survive, but you've got to multiply by the density-dependent factor PT, which says that the proportion that survives is going to be reduced by this factor as the density goes up. And then the final age class depends not only on the X2s surviving to age 3, but the X3s surviving because they're 3 years and older. So you'll see here we brought in all the Leslie matrix concept, the density-dependent concept, and the stochastic demography concept. And we have this model that we can now run. Now, there are a couple of concepts that come out of conservation biology and what's called population viability analysis. And one of the ideas that comes out of population viability analysis is that you have this coefficient that's called pseudo-extinction. And pseudo-extinction is the idea that when the population reaches a particular level, what you do is you say you declare it extinct in the wild, and all the animals that are left you take to some kind of facility where you can rear them, like a zoo. So the Arabian oryx, for example, became extinct in the wild, and the only animals that were left were animals in zoos. And what they did is that when there were so few individuals in the wild, then they may go and round them up and put them in a protected facility so they can breed them, and when they get back to a certain level, they can reintroduce them. So one of the big things in conservation biology is what's the best way to reintroduce individuals back in the wild. And you've probably seen either National Geographic or different kinds of movie series on TV that talk about reintroduction programs. And in California, one of the most famous was the California condor, where they took the birds, the last few birds that were left, put them in captivity, reared the eggs. They made these hand puppets so that the young would not become habituated to humans, and they would feed them from a hand puppet that looked like a condor adult, or at least sufficiently like one to make the program work. And and then they released condors back into the wild, and they're doing quite well. And then I talked about the debate of single large or several small reserves. And in order to think about this debate and to read about it, there's a paper here, How to Resolve the SLOS or SLOS Debate, Lessons from Species Diversity Models. And so this is a modeling paper in the Journal of Theoretical Biology that you can look at from 2010. And in order to understand what's going on, you say, okay, if suppose the probability of extinction in a large and a small area after 100 years, so in the large area, it's a lot smaller than it is in the small area. So what happens if I have one large area or several small areas? Well, if I have one large area, the probability of persisting in one large area is 1 minus P upon L, and the probability of not going pseudo-extinct in one small area is the probability that you don't go extinct in area 1 and in area 2. So if you're in two small areas, the only way you can go extinct is to go extinct in both. So the probability of going extinct in one large area is 1 minus PL, and the probability of going extinct in two smaller areas that have the same basic PS